So welcome back to Lecture 3 Part 2. In Part 1 we cover the basics of radiation damage, from defect cascades through to the formation of dislocation loops, voids and cavities. In Part 2 we're going to introduce the materials considered for nuclear fuels and the radiation effects observed. So let's get started. On page 31 of your notes you will find the basic requirements expected of a nuclear fuel. Those being good thermal conductivity, in order for heat produced through fission to be removed to the cladding and in turn the coolant. We want a fuel to have a high melting temperature so we can run our reactor as hot as possible, because that will improve efficiency. And finally, it's got to be mechanically stable. Now, given the importance of nuclear fuel in dictating the design of a reactor, its efficiency and its safety, a fair amount of money can be spent on its optimization, as relative to other costs, fuel cost is actually quite low. An obvious condition in our reactor design is that we have sufficient fuel to produce a sustained chain reaction. However, there are dimensional considerations we must take. Should we use a single solid block of fuel, the total mass of fuel in a reactor would be supercritical, and that would cause a runaway reaction, which is not something we want. However, if we split that monolith into sections and permeate it with a moderator, control rods, and a coolant, the fuel can be critical and have its heat efficiently extracted, whilst allowing for rapid shutdown of the reactions should it be needed when we drop our control rods in. So in most cases, nuclear fuel is in the form of plates and rods, clad in a corrosion-resistant material to protect it from the coolant. Now, as I've mentioned before, that there is a lot of nuclear fuel in a reactor. There's around 80 to 100 tons worth in a PWR, for example. And the images shown here on page 31 give you an idea of the size of a fuel assembly used in a PWR, around 5 meters long. And an important unit of power in qualifying a fuel rod is something called the linear heat generation rate, which is effectively the power per unit length of a fuel rod, and it's in units of kilowatts per meter, with a typical value of around 15 to all the way up to 70 kilowatts per meter. And this power of a fuel rod is principally limited by the thermal conductivity of the fuel, along with the necessity to avoid said fuel from melting. Now, obviously, it's preferable that we get as much energy out of our fuel rods as we can, keeping them in the core for longer, reducing refueling time and the amount of fuel needed. And this efficiency of how we use our fuel is typically quantified as well, and it's typically quantified as the fuel burn-up. And that has units of gigawatt days per ton. So how many gigawatts are extracted from each ton of uranium? Well, Generation 2 reactors originally achieved around 40 gigawatt days per ton, but with modern fuels and technologies, around 60 gigawatt days per ton is achievable. How? Well, the most beneficial advancement has been in the use of neutron poisons. These are highly effective neutron absorbers that can be injected into some reactors to reduce the activity of the fuel. Hence, the poisons are said to have negative reactivity. Okay? So why are they useful? Well, poisons, such as a boron carbide aluminium oxide mix, allows reactors to run for an extended period of time, as one can insert more fuel than is needed to achieve criticality, but add neutron poisons to control the reaction. And that will prevent the supercriticality that would occur should those poisons be absent. And because of that, the positive reactivity of the excess fuel is balanced by the negative reactivity of the poisons. And as the poisons are burnable, meaning their effects wear off over the lifetime of the reactor, then negative reactivity becomes less and less and decreases at the same rate that the fuel's excess positive reactivity is depleted. Now you might think that 60 gigawatt days per ton is really rather poor considering the total burnable energy available in a fuel rod. And you would be right. But that's because we actually burn very little of the fuel available in a rod, as I'll discuss later. However, should you use a breeder reactor and fission all heavy metal in your fuel, both fissile and fertile, burn-ups of up to 1,000 gigawatt days per ton are even possible. Should that modern thermal reactors take advantage of only a small percentage of the possible burnable metals, you're never going to achieve that, because modern thermal reactors don't take advantage of the whole potential of burnable heavy metals. They only take a small percentage. Another challenge with respect to burn-up is that it's not uniform across the reactor core, and it can differ across individual pins and across fuel assemblies, meaning that fuel assemblies must be moved around the core in an attempt to homogenize burn-up, at least to some extent. And this burn-up is often what radiation effects are measured against. And it is the radiation's effects on materials, most notably the nuclear fuel materials, that really is the limiting factor restricting the burn-ups you can achieve from your reactor design. So you can see that material science is really quite a critical area of nuclear reactor design. And as I mentioned in earlier lectures, uranium dioxide is the most common nuclear fuel, and that accounts for around 98% of all generated nuclear energy is from uranium dioxide. But metallic fuel is also in use, most notably in CANDU reactors and experimental reactors. So for completeness, let's take a look first at metallic fuels and see their advantages and disadvantages. Let's first look at metallic uranium. In the earliest designs, such as the UK's Magnox reactors, we used pure uranium. And metallic uranium is still being used today, like I said, in CANDU reactors, and unenriched uranium. The main advantages are you can pack more fissile material into the same volume for a metallic fuel, given their higher density. They're easier to fabricate and machine because of their metallic bonds. The thermal conductivity is excellent because of the metallic bonds, much better than for ceramics. And once you've finished, the fuel is much easier to reprocess, using, for example, electro-refining. On the other hand, metallic fuels melt at a much lower temperature than their ceramic counterparts or other competitors. And that's going to limit the efficiency of your reactor. There are a number of irradiation instabilities, which we'll cover shortly. There's poor corrosion resistance with reactor coolants, and then there's issues of compatibility with some cladding materials. Now, uranium is more abundant than you might think. It makes up around 4 parts per million of the Earth's crust, with the vast majority of the world's uranium coming from Kazakhstan, followed by Canada and Australia, with the projected amount of mineable uranium really quite considerable, though estimations range quite broadly and are dependent on several factors, which is way beyond the scope of the course. But you should also note that there's a fair amount of uranium that's obtained through reprocessing of spent nuclear fuel as well. So it's not all just fresh mined fuel, you do reprocess fuel. But remember that it's uranium-235 that is our key fissile isotope. And that only makes up around 0.7% of natural uranium, the rest being uranium-238, with a tiny amount of uranium-234. So what does uranium's crystal structure look like? Well, it has 3 of them. Alpha, its orthorhombic structure. Beta, its tetragonal. And gamma, its body-centered cubic phase. And those transitions occur at 669, 772, and 1132 degrees Celsius respectively. Now this raises alarm bells, because if we're going to operate our fuels at high centerline temperatures, when we're starting up and shutting down our reactor for pure uranium, our fuel's going to go through all these phase transitions, changing dimensionally and exerting stresses on the cladding and the fuel itself. So let's take a look a little bit more into that. What happens to uranium as you change its temperature? Well, let's look at a single crystal. Let's look in single crystal form, orthorhombic alpha uranium. It's strongly anisotropic. And the graph here, shown on page 34 of your notes, shows the temperature dependence of the lattice parameters for both pure alpha uranium and alpha uranium with plutonium. Now the coefficient of thermal expansion along the A and C axes are positive, but negative in the B axis. And that means along the B, well, it means as you increase temperature, the uranium expands along the A and C, but contracts along the B. And such anisotropy can cause significant problems should the temperature of the fuel change during reactor transients like startup and shutdown. Take a sample of polycrystalline uranium. That anisotropy, upon an increase in temperature, would cause neighbouring grains to change in shape in different ways relative to one another, meaning that they'll begin to exert stresses on one another and lead to localized plastic flow, and obviously the production of dislocations, which in some cases can even lead to cracking. Should our sample of polycrystalline uranium contain randomly orientated grains, when you heat it, you wouldn't see a net shape change. There would be no net shape change. But metallic uranium fuel is rarely untextured. In most cases, it's been rolled, and that leads to a phenomenon known as thermal cycling growth. Okay. And that's what we see here on the next page of your notes, page 35. What you see is the results of such thermal cycling growth. Here you can see a rod of uranium that's undergone different numbers of cycles. The top image shows the unirradiated bar and an irradiated bar after 1,300 cycles. The lower image shows the same unirradiated bar alongside a bar that's been irradiated to 3,000 cycles. And it just shows how the bar, over the number of cycles, how it's elongated so much that it's, almost like a candy lace. But not a candy lace I would recommend eating. Probably be hard to swallow, if you'll pardon the pun. I'm sorry. Anyway, so that bar was of a highly orientated, fine-grained alpha uranium, cycled between 50 and 500 degrees Celsius. Now you've got to understand that the term growth in this context means a shape change but constant volume. So you're retaining a constant volume. And this shape change comes from the movement of the grains in different orientations, combined with the stress relaxation of some of those grains due to creep and plastic deformation. Evidently, you do not want something like this to occur in your reactor. If you've got some fuel rods, you don't want them ending up looking like piano wire. So, how can we avoid it then? Well, the gamma phase of uranium that we showed on page 34 avoids this phenomenon altogether. Why? Because of its cubic crystal structure and the symmetry that comes with that. And through alloying with aluminium, molybdenum and magnesium, we can stabilize that gamma phase of uranium allowing it to be thermodynamically stable at lower temperatures, mitigating any thermal cycling growth. And the figure below shows the effects of just that type of alloying. You'll notice that notice the 4 to 8 atomic percent alloyed uranium at the bottom of the figure, displaying a far lower increase in diameter in comparison to the more pure uranium samples tested. And don't forget, these effects are observed regardless of if the material is irradiated. All these tests were done on unirradiated samples. We haven't even looked at the radiation effects yet. We'll leave that for our next lecture, along with the thermal conductivity, mechanical and corrosion properties, before we move on and look at metallic plutonium and thorium. So that's it for today, and I will see you for lecture 4, part 1 next time. Thanks very much. Any questions? Send them through. I'll do my best.